So it's my pleasure to introduce Nigel Clayton from University of East Anglia. You've got the lovely task of lecturing to science. So he's going to first of all talk about muons in chemistry training. Muons in chemistry, sorry.
Yes, you can see I even can get the title quite right, and I didn't put a line in the end of muons in chemistry. Anyway, the organisers give me quite a thankless task really, because I've got to try and tie together all the different possibilities of trying to use muons in chemistry outside of those which have been covered specifically in other talks. So semiconductors have been covered elsewhere, magnetism will have been covered elsewhere, and I noticed only a few days ago that charge diffusion is going to be talked about tomorrow. And that was, I had a little section on charge diffusion, so that was in my talk, part A. This is actually now part B, so I've adapted it slightly and gone back to an original talk which I had, which was less explicit on diffusion. So of course, I start off with just the basic question, why should you try to use muons? Well, I'm going to cover a bit more of this in the second talk, looking at the complementarity between NMR and ESR and MUSR. But essentially, why we're trying to use MUSR is because it's going to be an extrinsic probe. It's going to be something which we're going to add into the system as opposed to something which is intrinsically there, and that's therefore something that we can monitor. And we hope that we can then manipulate the way we're adding the muon in such a way to monitor what we're looking for. Why else use muons? Well, for a large number of years, people just had an interest in what does the muon do when it adds to a material. And in fact, Professor Cox spent a lot of time going through the periodic table, looking at all the different elements and trying to see what would happen to the muon when it added into the system. So there's just the intrinsic interest in trying to study muons as an exotic particle. How do they interact with matter? The next part I've put sort of the frame of the chemical problem, and this is of extreme necessity if you're going to be looking at a wider chemical system outside of those which I've sort of mentioned briefly before. That means you must look at your chemical system in such a way to work out what the muon is going to do in that system and whether you can get the type of information that you want from that chemical system by using muon spectroscopy. And that might mean that you have to add something into your system to make sure that you can have the muon add to some double bond, for example, in order to create a muonated radical. You have to make sure that the system is set up in such a way that you can be tackled by muons. And it may be that the basic chemistry that you have, you can't tackle by muons, but if you were to modify that system slightly, then you would be able to use muons as an extrinsic probe. So it's extremely important when you think about the chemistry involved that you actually put it in the context of trying to do muon spectroscopy. So the overall rationale for, at least historically, for trying to do muons in chemistry is that muons act as a light isotope of hydrogen. And a lot of the original work was based on that sort of premise, for example, looking at reaction kinetics, looking for kinetic isotope effects. And we touched upon that briefly. But then there's also the magnetic moment associated with the muon, and this comes into play with all the semiconductor, all the molecular magnetism, those sorts of things. But we're not going to be touching upon those really, except as that's part of how you use muons as a probe. But as with all other techniques, then you can use muons to study structure, dynamics, and kinetics. So this is just a very broad brush that you can tackle all these sorts of things. And what I hope to try and do in this talk is just to illustrate some applications of where you can use muons. There'll be a bit of theory along the line, but I'll skip those slides by and large because I want to show you examples. So here's just one very quick example just to illustrate what I mean by the intrinsic interest in muons. How are they going to interact with matter? In this particular case here, how it's going to interact with sulfur. So here's the muon adding either as a bond-centered state there or to, well, I'm not quite sure what this looks like, an end muon addition at the end there. But it's an S8 ring and the muon is added to it. Just what happens to it? And that was just the intrinsic interest in muon chemistry there. But what's going to happen to our problem? If you come here from the background of a chemist, well, essentially we're going to have some stuff there. We're going to implant the muon into that, and the question is, what's going to happen to the muon? How is it going to interact with that material that we're looking at? And there's three sort of possibilities that we can imagine what might happen to the muon. I'm not sure how much of this has been touched upon before, but we can have basically a diamagnetic muon, where the muon is going to be essentially trapped at some negative site, next to some negative site within the lattice. If you have oxide ions in there, it's going to be trapped next to those. Or it may, if you have some sort of if you have an inert gas, it may just be a free muon coming out. Then you've got muonium, where it's picked up the electron. That might be either from the material itself, or it may be, if you're doing this in water, it may have picked it up from the radiolysis trail. So that can be created a muonium. That muon, if you have a target within within your system here, you have some double bonds, then the muon can add to that and to create a muonated radical. This is the simplest type of muon addition, but you could have some sort of complex organometallic compound there, where the muon addition might not be quite so clear, but nevertheless you can form some sort of muonated radical. So we've got those three possibilities. This is just to go back to sort of historical aspects of muon chemistry, and these were the way in which these ideas were first developed in books, really old books like David Walker there, and so that's got an element of chemistry, but not so much, it's more on the radical side. Then we have some a more recent book, muon spin rotation, relaxation, and resonance. But again, this one is not so much chemistry, it's more sort of those other aspects which we pull from this talk and put elsewhere. But if you look at these sort of matches the sort of things that I put in my first slide there, so I won't go into those in more detail, but these are the things which came out historically. The things which are offering new directions to muon spectroscopy are the way in which you can try to modify the nature of the muon addition into the material, implantation into the material. So I'm not going to be saying much about all of these, or any of these. What I'm going to be just sort of showing maybe a couple of slides or two about the particular slide to illustrate where these have been used, just to give you an indication of the broad scope of muons in chemistry. So it can be used to study surfaces. If you have a low energy muon beam, such as at PSI, then you can implant the muon at the surface of the material, and that can be then used to study the dynamics of polymers at the surface. It can be used to look at soft matter, and here, for example, if you're looking at surfactant systems, you can look at the partitioning of a muonated radical across different phases within that material. Then there's a series of combination experiments, and these are quite interesting ones, where you're going to combine the muon spectroscopy with some other technique. You might combine it with an electric field or some sort of laser irradiation. So you're doing more than just observing the muon, you're trying to modify the system in some way or other in order to highlight something specific about the chemistry which is going on. And lastly, you can couple this with high pressure and temperature cells, so you can look at extreme environments. So you're not just limited to looking at things at room temperature. So what can be determined? Well, we can determine something about the nature of the muon species, the number of species, the functional forms of decay, the decay constant, hyperfine coupling constant, if you have a muonated radical. So these are all the sorts of things that you'd get from your experimental system, and you're going to try to learn something about the chemistry involved from these different aspects of the muon decay. So now I sort of want to go in, split my talk into three parts here, just to look at the different ways in which the different types of muons can be used within chemistry. So start off with, first of all, with diamagnetic muons. And I'm going to do a very simple sample, which sort of is very closely related to the talk that you'll get tomorrow, which is going to be looking at charge diffusion. Only in this case here, what I'm interested in is whether you can actually study the dynamics of the implanted muon. So the muon itself is going to be diffusing. Again, I'm not going to spend too long on this, simply because, as I say, this is going to be covered in more detail tomorrow. So in this case, the idea was to take this system here, which is a zirconium phosphate, organic zirconium phosphate, which is a hydrate. This shows proton conductivity, and the question was, could you use muons to try to study that proton conductivity? What was taking place? So the idea here was to try to implant the muon and to see whether you can then look at the diffusion of the muon. In this case, it would be a diamagnetic muon, principally because this material is an insulator, and because the chemistry of similar systems would suggest that you should trap this as a mu plus, not as some muonium or some other species there. So what's going to happen is you're going to have a Nu plus, which is going to be trapped near an oxygen. That's the idea. Or you could have some sort of abstraction reaction taking place into mu OH. What we're going to do then is to monitor the muon decay from and look at the local nuclear magnetic moment, the dipolar field from that. Because what we're going to see is this muon moves around, then it's going to reduce this local nuclear dipolar field. But in all these systems, the problem is, do we actually know that we're not going to form muonium? How do we know that we're actually going to form this mu plus species, this diamagnetic muon? This is just a sort of schematic of the thermalization trail that you're going to start off with a very high energy muon going into the system, something like 4.1 megaelectron volts, and it's going to come out at the other end at sort of thermal temperatures. So you're going to have along the line a whole lot of electrons and gain of electrons. You're going to have a whole series of different events there. How do we know that we're actually going to not end up with a mu dot or a mu plus? How do we know what it's actually going to be at the end? And this is the one basic problem with a lot of chemistry. If you're trying to study these systems, it's very difficult to predict, certainly with any complex system, what you're actually going to get as the product at the end, if you're going to try and target one particular type of species there. So this thing, I'm sure you'll have been through this sort of thing. How do you know what you've got there, whether you've got a diamagnetic muon or a muonium, something like that? Then you check the asymmetry to make sure you don't have a loss of the asymmetry. So in this case here, we get a total asymmetry which is about 21.8%. So it doesn't look like that we've got any magnetic fraction or missing fraction. So the first thing you're going to do is check the symmetry, and I assume that this sort of thing you'll be going through this in data analysis. That's why I'm sort of skipping through this quite quickly. But these are the sort of things that you would need to do. You need to check that you've got something like the full symmetry, and that the rotation frequency that you get is going to be typical of a diamagnetic muon, and that should always be the case. That you're going to essentially have a diamagnetic population of 1. Well, that's going to be probably an extreme example, but that's what you're looking for. So you'll be looking for no evidence of muonium, and that you'd look for in a repolarization to see that the muonium fraction is 0. And then in all these systems, there's also that little bit that you can't explain, that missing fraction, where you don't know quite what's happened to it, but it don't have the full signal, you don't recover the full signal by repolarization, and you can't explain it all by the diamagnetic system. So you have one major effect can be depolarizing encounter with a paramagnetic species. Well, what is this likely to be? Well, the most likely cause of this is going to be if you have a liquid sample, something like that. It could be just oxygen. You've got dissolved oxygen. So that's why it's crucial that in any types of systems like this, that you have thoroughly deoxygenated systems, because otherwise you can just lose your muon in this sort of encounter here, and it becomes part of your missing fraction, and you get no information whatsoever. So this sort of is a very simple thing you have to remember. We're talking about diamagnetic muons, and this sort of overlaps with a bit when I talked about complementary techniques. Can we use the rotation frequency? After all, if you're thinking about trying to do a diamagnetic muon, you should have some sort of chemical shift information. It should tell you something about where that muon has implanted. If you think like NMR terms, that depending where that material is, it has a slightly different chemical shift. So surely this muon, if it's in a slightly different electronic environment, ought to have a difference in rotation frequency. Well, the problem with this is that it's severely limited by the muon lifetime. And this lifetime, you'll have come across, is about 2.2 microseconds, and this leads to an uncertainty of frequency of about 0.72 megahertz. If you compare that with the size of proton chemical shifts, which is what we'd be looking for in terms of the magnitude of these effects, 10 to the minus 5 megahertz. So you can see these two are orders of magnitude apart. Just the intrinsic line width you see for a muon signal means that you're not going to see chemical shift information from muon spectroscopy. Well, in general, there is one exception to this. This is a muon night shift. If you're looking at some metal, you can see a muon night shift, And the reason for this is because the interaction between the muon and the conduction electrons gives rise to a very large change in resonant frequency, and you can see that by the size of these values, these shifts in ppm here. So 600 ppm, if you think about the normal proton chemical shift range, is 0 to 10 ppm. So you're a couple of orders of magnitude, or at least an order of magnitude bigger in terms of the frequency shift there. So you can see then a change in the resonant frequency if you have a night shift. And that means you can look at density of states at the Fermi level. If you're interested in trying to study a metallic aspect of a material, then you can hope to get some sort of information on the muon night shift. So how do we tell diamagnetic muons apart? Well, essentially, we have to look at the size of the local dipolar field. So we have to obtain that from the relaxation time constant, propose some sort of structural model based on the chemistry, and search the crystal structure. So if we're looking for maybe more than one site, and really it's going to be difficult to say if it's going to implant more than one site, we're going to be looking for a number of different relaxation times, maybe 1, 2 relaxation times. So that complicates what's going to happen. You're going to have to do an analysis of the decay. All right, so let's go back to that system which I was talking about. What we want to look at is whether the muon is going to be diffusing through the system. We're trying to look at some sort of charge diffusion. And so here we have the decay that was observed, and we then fit that to a 2 exponential, 2 Gaussian decay there, and we can see two components, one with a very fast relaxation and one with a very slow relaxation. So this would tend to suggest we've got two different sites that the muon can implant into this material here. And then we can then try to say something about where those sites are, dependent on the magnitude of these local dipolar fields as determined by these relaxation rates here. So essentially this one here is a very large value, which suggests that this is going to be near a nucleus spin with a high magnetogyrate ratio. In this particular case here, it's going to be near to a phosphorus or something like that, because the oxygen won't have any dipolar field. It's principally spin 0 for oxygen 16, and well, the other one would be the hydrogens. If it's nearby to another hydrogen, this is going to contribute to the local dipolar field, so kind of nuclear. So you can say something about where it is by just localizing it through calculation. I'm not going to say much about this because this is simply, if you're going to interpret these sort of zero field decays, then you use this Kubi-Travi function. The reason I'm not going to say this is because this is going to be touched upon tomorrow, so this is going to be essentially the charge diffusion. But what we do here is to just to fit this decay now here to a Gaussian Kubi-Travi decay there, and we can get these two constants here, which you can see is rather similar to the Gaussian analysis, Gaussian decay analysis that I got before. But only the relative proportions of the two are roughly the same now, and but the decay constants are rather similar, which is what you would expect really, because these are determined by the local nuclear dipolar field. So these two different types of analysis shouldn't give you really two different results there. But the crucial thing here is that you see essentially up to about 300 degrees C, you see essentially no temperature dependence in this line shape at all, none whatsoever. Well, maybe a slight reduction in this one here, which is essentially saying that in this particular system at these temperatures, the muon isn't diffusing. So in this case, it's rather a negative message that it's simply that this is consistent with the low proton conductivity. We'd have to study this at higher temperatures in order to look at this conductivity in closer detail. But the problem is with this system, you can't. If you go to high temperature, it dehydrates. And if it dehydrates, you lose the water and the conductivity falls off. So this just shows what happens if you dehydrate it. If you dehydrate it, you lost the water there. What happens is that most of it now goes into a site with just a simple, smaller dipolar field associated with one of the types of muon products in the system there. So we've lost the fastest decaying component, which presumably then means the muon added to the water. So added to the water, and we simply see the remaining slow decaying muon, which is trapped by the OP. So that just simply shows that this decay here is very, very slow. There's a very low dipolar field. So I've got something about interpretations of delta. If you carry out this analysis, the muon is implanted into the system, you watch the decay, you measure the decay, you know what the magnitude of the local dipolar field is. How does that tell you where that muon has gone? Well, you have to try and find some sort of model system perhaps, or you can take the crystal structure, try and implant the muon in likely places, or you can do more sophisticated calculations to find where that muon is likely to implant, in order to then calculate what that local dipolar field would be, and that would then tell you where that muon is implanted. So it's rather, you can't really say much about where that muon is implanted independently of these sort of calculations. But this is a very simple type of analysis, just to try to work out what type of muon species you might have if the muon has added to the water in those systems here. So here were some model reactions in ice, and here some hydrated crystals where different types of muon addition to water had been proposed. So here you form essentially a hydronium type ion, and there all you're doing is substituting one of the hydrogens. So these two different systems for two different hydrated crystals suggested two different possibilities there might happen. And so these were very crude calculations. You just calculate the second moment, won't need to go into that, and ultimately if you search through the different sites, then you can see some sort of comparison here between the different crystal sites that you might have for the proton. So these are all the different proton sites that you can have in this zirconium phosphate dihydrate. So they're labeled 1, 2 to 6. So 2 are associated with the phosphorus, the others associated with the waters. And here this is a substitution product, so H mu O. You can calculate then what the second moment would be like, and you can then compare that with the values that you see experimentally, and it looks like this delta 1 looks very similar to this H3, which suggests that you do form some sort of substitution in water. But you can get some sort of rough idea of where the muon has gone simply by looking at the second moment. So this simple then, this system there, which is probably characteristic of diamagnetic muons, what you tend to do is implant it. You then try to look at the diffusion of that, or either use that implanted muon as to look at the diffusion of other ions. It's rather a limited range of things that you can do with the diamagnetic muon. So this is just the quick summary here. The thing is, this really sums it all up here, that we're going to, the temperature dependence is then indicative of the muon dynamics. And the reason for this is because you don't get chemical shift information from the muon, and so all that you're really left with are these sort of relaxation type properties. So the next category are muon and muonated radicals. So what's the difference here between muons and the diamagnetic muons? Well, the essential difference is you've got an unpaired electron there, you've got a paramagnetic effect there with the electron coupling to the muon, and that can give rise to very large interactions. So the important thing to get from this slide really is just how big the interactions are between the muon and the electron. It's hard to find interactions. So these are tens of hundreds of megahertz. And it's these very large signs of interaction which means that you can get a lot more information from muonated radicals than you can possibly get from the diamagnetic muon. And that's why these type of species are much more useful in the broader sense of trying to study chemistry than the diamagnetic muon. So here will be the precursor. The first thing you're going to form in the system would be the muonium, and this would therefore give rise to this species here, where you have a really very large hyperfine coupling constant here between the muon and the electron, 4.4 gigahertz, extremely large. Why is this interesting? Because the reactive chemistry is very similar to H dot. So you can think about this as simply like H dot. This can then react with whatever compounds you have in the system, and you can monitor that reaction taking place. And that forms the basis of one of the experiments that you're going to be doing, one of the practical experiments you're going to be doing. So in many ways, this is just like hydrogen. The ionization energy is very close to the ionization of hydrogen atom. The Bohr radius is very similar, so it's a very good analogy. And the mass, though, of this is very much less than the proton, so you can get a very large kinetic isotope effect. But of course, if you've got something in your system which can then react with the muonium, as for example a double bond, then you're going to get muonated radicals. So the muon here can add across the double bond, and therefore you're going to get this type of species here. And the muon hyperfine coupling constant here can expand, can range across a very large range here, as I sort of earlier said. So if it just adds across the double bond here to the oxygen, typically these are much smaller, about 10 megahertz, but add to something like a benzene, 500 megahertz. So these are very large interactions, which would make these really quite reasonable probes for trying to study whatever process you're interested in terms of the chemistry of the system. So how do you know if you have a paramagnetic species? Well, the full asymmetry is not seen in these transverse field, 20 Gauss transverse field experiments. This is just a simple note to say, why not? Well, it's because of the finite width of the muon part. Essentially, this species, the muonium species, dephases so quickly during the time between its formation and the first data acquisition that you've lost all information about it. So the simple thing is we can't find anything about it. So how do we know anything about that? Well, as I said, we have to do some sort of repolarization experiment. Again, I'm not going to say anything about that, because we don't understand about that, get in the way here. Or if you're going somewhere like PSI-Trump, then you can look at the precession frequencies. So are we muonium or muonated radical in our system? So ICES has said, if it's muonium, we're going to have a very large field for repolarization, whereas at PSI-Trump, where you have a continuous beam, then you have a high precessional frequency at low transverse field here. So this is just two examples here where you have two different hydrates, and the question is, what is happening to the muon when it's implanted into these systems? How do you know where it's gone? Well, in this case here, just look at the frequency range in 100 Gauss. So this is an 100 Gauss transverse field, and you have a resonance frequency of about 150 megahertz there. So that is indicating there that here, in cyclopentane hydrate, the muon has implanted as muonium. But it's a very small transverse field to get this frequency up here. Up here, there's a very similar type of frequency there, which is demonstrated there, but this is now in a 14.46 kilogauss transverse field here, so this is 2,5-dihydrofuran hydrate. So in this case here, it's now as a muonated radical. So what's happened here is that the muonium, in this particular case here, is stable as the muonium. Over here, it's essentially reacted with the 2,4-dihydrofuran hydrate to form a muonium ion, a muonated radical. So you've got two different species in these two systems. But this is partly the things which I was saying about the problem in trying to analyze what's going on. How would you know this system here and this system here? Why is one giving you the muonium and why is it giving you a muonated radical? What's the difference between these two? Why should you get this difference? Well, you have to think back to the chemistry which is involved in the system. I won't do that. So what can you do by studying the muonium? Well, you can look at the relaxation rate at low field. You can just look at the decay of the signal there, and you can get some information about the reaction kinetics. If you go to higher fields, then you can measure the muon hyperfine coupling constant, and you can then say something about where that muonium has gone in the complex system, because the hyperfine coupling constants tend to be solvent dependent. So you can say where that muon is implanted. And here's just a very simple slide to show how you would measure muon reaction rate. So the idea here is what's happening is that muon is implanted into the system, and it would show an intrinsic decay rate. And that intrinsic decay rate here is lambda naught. So this is in the absence of any other relaxation mechanisms here. So that's just the intrinsic relaxation rate of muonium in a pure solvent. And remember, this is going to be a deoxygenated solvent, otherwise this is going to be far larger than you would otherwise have hoped. You can then add some substrate here, which is then going to react with the muonium, so something with a double bond, for example. the muonium will then react with this system here, and in reacting, it's going to essentially hasten the decay of the muonium signal. You're removing muonium from the system, and that will appear as an excess relaxation rate. So what you'll find is the true relaxation rate is then going to be this observed relaxation rate, should I say, is going to be the intrinsic rate plus some sort of rate constant here, and by varying the concentration here, then you can get some varying the concentration there and plotting that against the observed rate there, then you can get some idea about the reaction between the muon and that material that you've added to the system here. And this then tells you something about the rate window that you have for this particular process, and it just shows you what the biomolecular rate constants have to be in order that you can observe this by muon spectroscopy. So this is essentially going to be limited by the time constant for the decay of the muon. So here's some just an experimental tip that you can see there. And here we see some more data here, just showing how this has been used experimentally to look at the reactions between muon and hydrogen in different systems here, addition to benzene to get the cyclohexadiene radical. You can see there that the muon addition is much faster than using hydrogen or deuterium there. You can then look at this in extreme environments if you want to. So here's an example of by having a carefully designed reaction cell here. Remember, this has got to be something which is going to be capable of looking at high temperatures, and yet it's still going to have a window in which this muon can implant into the system there, and it isn't just stopped by the vessel which is holding the sample here. You can then study it at an elevated temperature and pressure, so in supercritical water or something like that. And here is the reaction rate you can see between muon and benzene under different conditions. This was an example which there is just illustrating the way in which there seems to be something happening at a higher temperature as you go through this phase diagram here. This is just extrapolated from low temperature data there, which admittedly is a very small number of data points up there, but this was at higher temperatures and pressures over there. So you can see, you can study reaction kinetics, the addition of a muon to this particular system at quite extreme environments. And there's a whole compilation of muon relaxation rates. I must admit, I haven't checked this reference, this website lately, so it's a couple of years old at least, so I hope it's still there. But people have been using muons to try to study addition of time. Okay, so combination experiments, again, this is sort of flicking through a whole range of different types of experiments really very quickly. And I appreciate that this is a lot to take in, but what I wanted to try and do is just to illustrate the range of different ways in which people are trying to manipulate the system in order to try to study things by muon. In this particular case here, they were trying to look at the potential energy surface associated with the reaction between hydrogen and the muon. So it's the simplest possible reaction that you might have. So you have molecular hydrogen reacting with a muon. In this case here, they try to excite the hydrogen up to the vehicles 1 vibrational energy level to look exclusively the reaction between this vehicles 1 and muon. So it's looking at the muon in excited, the hydrogen in a vibrational excited state as opposed to just in its ground vibrational state here to study the potential energy surface sort of in non-equilibrium state. And the way they tried to do this was by a laser excitation method in which they were exciting this up. And you can see here that they have a laser on, laser off, which should show a difference. Because if you're creating things up into a higher vibrational state, then you should get some sort of different reaction than if it's in the lower vibrational state here. Now, the authors themselves, when they presented this data, said that it was preliminary and needed to be refined to get better signal to noise. But what they had seen, and perhaps you can see it with the eye of faith here, with a fit. This is a fit here, the difference between the laser on and the laser off, and they have a reaction rate here, which presumably is the reaction in the higher vibrational state with the muon. Now, whether that's true or not, I'm not entirely convinced because it does look rather noisy data. It looks pretty nice with that fitted line going through, but can't, if you took that line away, I must admit, given the noise there, and given the signal noise ratio as shown by the size of those error bars there, I think that's probably with the eye of faith really, that they found that out. And as far as I'm concerned, as far as I'm aware, this hasn't been repeated. They haven't tried to repeat this to get improved signal to noise. And I think intrinsically it was a very, very hard experiment to do in order to ensure that you get sufficient excitation of hydrogen into this higher vibrational level uniformly across the system where the muon is being implanted is a very difficult problem. I think that was one of the difficulties that they had. But nevertheless, what this shows is that you can think of trying to do experiments where you're going to study the muon chemistry in the system under laser irradiation and look at what's going to happen to the reaction with the muon. So here we have a very quick summary then, that so with muonium, then what you're generally going to be looking at, this is going to be some sort of a radical reactive immunated radical. But what we can look for then is that we can look at kinetics, so the reaction between muonium and some species that we have present. We may be looking at diffusion, and we can get these from excess relaxation rates there. You can say something about the system, whether you've got muon or muonated radicals, by looking at the precession frequency there, or when you have high repolarization field analysis. So there's an extensive database of muon relaxation rates, and the novelty here is that you can study these reactions under extreme conditions of temperature and pressure. So the final bit I wanted to talk about in terms of the chemistry is to look at muonated radicals. Now, I've already said that this is perhaps the closest you can get to trying to think about the analogy of using chemical shifts or hyperfine coupling from ESR, because you can actually see chemical resolution in your species through the nature of the hyperfine coupling constant. That so far we haven't really had that chemical resolution. You've been trying to guess where things are or calculate where things are, and you haven't been able to generate those things beforehand. So in this case here, as opposed to where I say the muon implants into the system and you work out where it's been trapped, you hope it's going to be trapped somewhere that you're going to be able to use. You can't necessarily force it to be trapped in that place here. In this case here, for muonated radicals, what we're going to be doing is adding something, or already having intrinsically into our system a target in which that muon is going to interact, muonium is going to react to form that muonated radical. So that's the advantage here. So we're going to choose our system to generate the species that we want in order to study some aspect of the chemistry of that particular system. And all that we need, in general terms, is the presence of an unsaturated carbon center. Now, you can have this in more complicated type of radicals, adding it in different types of systems, which I'm not going to be talking about. Here I'm going to be looking at just purely carbon-based radicals. So the idea is that you can have these either intrinsically, as I said, that maybe you're already looking at a system where you have some double bond species already present, and so you wanted to monitor what's happening to that species there, and therefore you can then use the muon to create the muonated radical. Or you can add the target. For example, you could add benzene to the system, and that will give you a immunocyclohexadienyl radical very efficiently. And the most obvious thing about this information is that the hyperfine coupling constants are sensitive to the environment. Mainly this has meant that you can tell what sort of solvent phase it's in. Is it in an organic phase? Is it in an aqueous phase? Where is that muonated radical gone? You can then monitor what's happening to that muonated radical. Where did it go? What's happening to it? By looking at chemical exchange processes or dynamics averaging the hyperfine coupling constants. And as before, as with muonium, then if there's some reactions with this muonated radical, it's then going on to react with something else, then kinetics and dynamics can be obtained from excess relaxation rates. So this would be rather similar. If you generate a muonated radical and it reacts on the timescale of a muon lifetime to some other species there, then you can monitor that reaction through this excess relaxation rate, as I mentioned with the decay of the muonium signal. Well, how do we study these muonated radicals? Well, the best way of trying to study these is by a technique known as avoided level crossing muon spin resonance spectroscopy, ALC mu-SR. Now, I'm not going to go into the great detail of the theory behind this. All we need to know is that this is a good way of trying to study radicals, because we tend to see a large number of different resonance positions depending on different proton hyperfine coupling constants. And the example I'll show will illustrate how this is the case here. It generally gives you better signal to noise, so it gives you improved count rate, and there's no decomposing problem with the slow-forming radicals. Another bonus about ALC is that you get essentially 3 different transitions, of which only the 0 from 1 are the most important. But these tell you something about the dynamics. Simply by the observation of these, you can tell something about the dynamics in the system. You rarely see the delta M equals 2. What we can forget about most of this diagram, all we need to realize is that there are going to be 2 main transitions. There's going to be a delta M equals 0 transition, and this is observed wherever there's isotropic motion. So wherever isotropic motion, then you're going to get this delta M equals 0 resonance there. You'll also get a delta M equals 1 resonance if it's a solid, or if there's some sort of anisotropy to the system which isn't fully removed by the dynamics. So this line is a sensitive indicator of reorientation dynamics on this sort of time scale, the 20 to 50 nanosecond time scale. And why this time scale? Because it goes back to the magnitude of the hyperfine coupling constant that you're involved with. So you see these two sorts of lines there. So you can look at mu-naked radicals, and this is rather an interesting example because it goes back to the same idea of spin trapping. Rather than using the muon itself directly, so to speak, what you're trying to do is to say something about this keto-enol equilibrium in water at high temperature and pressure. But you're not looking at these directly. What you're going to do is to trap these by reacting with the muon. And you can get 2 different possible addition products. So in this case here, if the muon adds to this system here, then it's likely to be an oxygen addition product with a smaller hyperfine coupling constant. If it acts to this enol form, then it's going to trap the enol form by addition to this double bond there, which will give you a much larger value for the hyperfine coupling constant. So you can tell what species is formed by the magnitude of the hyperfine coupling constant, and therefore you can tell which of these 2 forms you've trapped out in the species, and you can work out what the equilibrium constant is going to be. So this, as I say, this analogy is with spin trapping in ASR, and it's very clear that you can see these differences in the hyperfine coupling constants over here. So if you look at these 2 systems here, look here, this is at 92 degrees and 136 bar. The resonance field here is about 1.4 kilogauss. Up here, the resonance field is about 10 kilogauss up there. So there's a marked difference in the ALC resonance field that you see in these 2 particular cases, depending on whether you're going to see the enol form or the keto form. And this will then allow you to study this equilibrium constant as a function of temperature at high temperatures and pressures. And this is the data, so you can see the formation of at low temperature is mainly the keto form there, and at high temperatures then you're forming a lot of the enol form up there. So you're seeing the way in which this keto-enol equilibrium is being disturbed, and just using the muon then to trap which of the 2 species are being formed. So it's a slightly different type of use of the muon. You're not really so interested so much in the product, only insofar as it tells you what the precursor was. So the last example which I've got is which sort of combines the look at the effect of different types of mu-naked radicals and illustrates how you can get a number of different resonances, is to look at this problem of interfacial transfer. So what we're doing is essentially a dynamics experiment. And what we're going to be looking at is going to be a mu-naked radical, which is going to be exchanging from one medium, water, into another medium, into heptate. So these 2 media, what will happen is that the muon hyperfine coupling constants are going to be different. So what we're going to be using then are the muon hyperfine coupling constants, and as they are perceived in the ALC spectrum, to monitor whether the muon is in this environment here or in that environment there. and through a process of chemical exchange, averaging of those hyperfine coupling constants, we'll be able to say whether it's crossing that barrier there and how quickly it's taking place. So here we can see what I meant about seeing a number of different resonances depending on the hyperfine coupling constants, the proton hyperfine coupling constants. Because we've got these two radicals here, we don't have two possible radicals, either the muon adds at the end there or it adds at the end there. So you can see these two possible radicals there. We actually only form one of these, which is not really clear how this is drawn out. I think the numbering seems to have gone up all over the place there. But what is happening is that we're seeing these different resonances corresponding to these different hydrogens that you have in these radicals. So for each of the different hydrogen environments, you've got a slightly different unpaired electron density, and as a consequence of that, you've got slightly different values for the resonance field required to see depolarization of the muon signal. Well, this has been touched upon. Another speaker has talked about this anyway, so I'm not going to be talking about trying to do calculations. So there's some calculations there, you can do them. But this is the interesting thing here. So here we're seeing one particular peak in that ALC spectrum. If you look at heptane, it has this value here for the resonance field. In water, it has this particular value here. So we see two different values for the hyperfine coupling constants reflected in the different resonance fields required for depolarization. If you look at the system that we're actually interested in, the microemulsion, then we see something which is essentially bang in the middle between these two lines. What is happening then is the muonated radical is essentially exchanging between the heptane and the water environment within the time scale of the ALC experiment, so that all we see is the average hyperfine coupling constant. So that is an example where we're seeing a dynamic process taking place. This are simply some calculations which were carried out. These were actually carried out using a Monte Carlo program. We simulated the ALC spectrum. You can do this by using quantum, but you can simulate what effect you might expect to see in the ALC spectrum as a function of the exchange rate. So if the exchange rate is slow, you see the two separate hyperfine coupling constants. If you have intermediate exchange, then you have a broad resonance, and if you go into the fast exchange, you see a single sharp resonance. We're in the fast exchange resonance regime. Fast exchange resonance regime. Anyone who's done NMR, looked at chemical exchange, these should be entirely familiar. Upside down perhaps, but these are entirely familiar with the line shapes that you get for two-side exchange in NMR. So all that we're doing is then looking at an exchange process. We can then simulate the data and we can get a rate for the process. So the final slide, sort of goes yet a different track here. So that was looking at the dynamics of diffusion of a radical, of a muonated radical. In this case here, what it's trying to look at are the dynamics associated with a muonated radical. Now what we have here is looking at polystyrene. Polystyrene, you've essentially got aromatic rings. What can happen is the muon can add to those aromatic rings to create what would be a cyclohexadienyl radical, a muonated species there. That then is going to be able to report on the dynamics available to the polystyrene at a particular temperature there. So what we can see here is that in this particular case here, that depending on where you implant the muon, so you're able to vary the muon energy so you can define where the muon is going to implant, then you can see that you have a different relaxation rate depending where the muon is implanted into the material. So where the implantation depth is deep into the material there, then you see a relaxation rate which is typical of the glass transition temperature. So that's why it's been labeled lambda G. So it's essentially the bulk glass transition temperature. So you have a more static value for the relaxation rate there. Whereas if you go towards the surface, well, the muon, where essentially you have a higher glass transition temperature, a lower glass transition temperature, you have a more mobile muonated radical, and therefore you have a different relaxation rate there. So what this is simply saying is that you can monitor the dynamics associated with a muonated radical, even in a complex thing like a polymer, and you can study it as a function of depth within the material by just simply varying the muon energy. Now these sorts of experiments were carried out at PSI, but nevertheless this just shows the scope of types of experiments that you can carry out. Well, I've really rushed through a whole range of different types of applications, and I appreciate I've sort of covered a lot of different types of material. But just to summarize what I've done here, for muonated radicals, these are going to be formed by reactions between muonium and unsaturated centers. And we can either have an intrinsic unsaturated center, or we have an added target molecule. We can then identify whether we have these muonated radicals through depolarization and look at the hyperfine coupling constants. We can monitor radical kinetics and dynamics through the relaxation rate, looking at the excess relaxation rate. The hyperfine coupling constants are sensitive to the environment, and then we can look at the location exchange between sites, and the ALT delta 1 resonance of the shape are sensitive to dynamics. I didn't really show this one, but in my next talk, when I'm looking at the complementarity between NMR and ESR and MUSR, I've got something which will say something about this. Okay, well, I think it's probably time for a break now, and I appreciate, again, I apologize that I've covered a wide range of different types of systems, but that's intrinsic to the nature of the way in which you're going to apply muon spectroscopy to chemistry. It depends very much on the particular system that you're looking at. It's not a very general technique, it's a very specialized technique, but you have to look carefully at what the chemistry is involved, how can you modify your system in order to find out what information you want about that particular chemical system. So thank you very much for listening.
Thank you, Nigel. Are there any questions? The list is perfectly clear.